Okay, so we're looking at the Alkene table. This is row 3, where you've been given the condensed structural diagram. We'll work our way to the other columns, filling everything out. Perhaps the easiest one to work to would be the structural, and then from there we can do everything else. So the structural, remember, you're just going to be converting to the more expanded version. So if I count up the carbons, 1, 2, 3, 4, 5, that's how many start in my structural diagram. They're all connected by at least a bond. Remember, we're in the alkene table, which is suggesting that there's a double bond. We have to kind of interpret where that is. So if we look at carbon 1, there's 3 hydrogens. We look at carbon 2, 2 hydrogens. We look at carbon 3, 2 hydrogens. We look at carbon 4, there's only 1 hydrogen there, and there's only 2 hydrogens on our last carbon. So there's a deficiency of bonds. These carbons right here, 4 and 5, only have 3 bonds. So the way that we have to interpret this is that in order for them to be full, have their full octet, we actually need a double bond between them. And that's what makes this an alkene. Now, from this point, we can probably work to our line diagram or name, whatever we prefer. So with our line diagram, I'm just going to do it right underneath. Remember, a line is used to indicate the carbon-to-carbon bonds. So there's your line from carbon 1 to 2, from carbon 2 to 3, from carbon 3 to 4, and from carbon 4 to 5. But this is a double bond. So that last line will actually double up and indicate it as a alkene, a double bonded carbon. Okay, and we also have to name. And this is where things get a little bit trickier when naming, because we can't just count our number of carbons and throw "ene" on the end. We actually have to tell where that double bond is. So the first thing we can come up with is our root name. We've got 1, 2, 3, 4, 5 carbons. 5 carbons is associated with the root name pent. We also know that there's a double bond somewhere, so that changes the suffix of the name to "ene". Now, we would have seen in the PowerPoint slides that that double bond can potentially be in other locations. It could be here, could be here, could be here. We have to indicate where it is. So a lot of times I find that working from a structural diagram is easiest when we're trying to indicate where the position of the double bond is. Remember, it's going to be a number that's stated up front to tell you the location of the double bond. It needs to be determined where in the molecule it is, specifically closer to one end, let's say. So the way we try to identify this is number our carbon chain from left to right, so 1, 2, 3, 4, 5, or number from right to left, 1, 2, 3, 4, 5. Remember, these molecules are 3-dimensional shapes, and I could pick this up and flip it around if it was a structural model. I always want to look at it where the double bond is closest to the beginning of the molecule, and that would be achieved by flipping this over. The other way to figure that out is to number in reverse, and we can see that that double bond is between the first and second carbon. That's the best way to look at this molecule, rather than it between the fourth and fifth. So if it's between carbons 1 and 2, we use the lower of those two numbers, and we say, this is 1 pentene. Our double bond is between carbons 1 and 2.